Bien, buenos días. Gracias en primer lugar por su asistencia. Mi nombre es Pedro Hernández, soy investigador del Instituto Tecnológico de Energías Renovables ITER y actualmente formo parte del equipo del Instituto Volcanoes de Canarias. Y el motivo de nuestra presencia aquí, primero también agradecer a Antonio, pues que nos un poco organizara este seminario. Es un poco, creíamos que era interesante que mis colegas Seigo Miyamoto, él es investigador del Instituto de Investigación de Terremotos de la Universidad de Tokio, y Valeri Tioukov, que es del Instituto Nacional de Física Nuclear de la Universidad de Nápoles, pues presentaran pues un tema bastante novedoso, es un campo de investigación bastante reciente que se ha aplicado pues en Japón, en volcanes japoneses y recientemente también en volcanes italianos, que es lo que ellos llaman pues la radiografía de volcanes pues a través de los muones, ¿no? Nosotros hace un par de años, a mí esto, yo soy químico, o sea, esto me sonaba totalmente a chino, pues me enteré a través de unos amigos japoneses del trabajo de este grupo de Tokio y pensamos que era muy interesante pues poder aplicar esto pues en volcanes aquí en Canarias. Uno era el Teide, habíamos pensado también el tema de Cumbre Vieja, tiene un montón de aplicaciones, ¿no? Y solicitamos un proyecto al gobierno de Canarias, conseguimos pues dinero pues por lo menos para empezar a hacer este estudio y el año pasado tuvimos la visita de Miyamoto. Ramón García pues nos tuvo la amabilidad de enseñarnos las instalaciones, nos ofrecieron también ese pues apoyo del Instituto Astrofísico pues en aquello que fuera necesario, ¿no? También por la experiencia que tenéis aquí. Y hace unos días pues hemos instalado el primer detector para hacer esa radiografía de lo que es todo el cono sumital del Teide, ¿no? Entonces, esa es la razón de por qué están aquí. Y para mí la verdad es que es muy gratificante ver, pues pensamos que era interesante, pues eso, tener una discusión con ustedes que saben de este tema bastante y ellos estaban muy entusiasmados pues poder compartir lo que están haciendo y tener este seminario, ¿no? Yo por eso les agradezco de verdad la asistencia, ¿no? Y él va a hablar en inglés, igual también que Valeri, y ya yo les paso la palabra. Gracias.
Hola, it's my pleasure to come here and to talk about my study, muon radiography. So, at first, I will talk about the basic principle of muon radiography, and second, I will talk about a little bit about muon detectors, and third, I will show the past and recent works. And finally, let me introduce our going on projects. The principle of the muon radiography is very similar to X-ray examination of our body. So please imagine that there is the X-ray source, and our body is here, and here is the X-ray films. And X-ray films is in the X-ray examination. The beam source is X-ray. The beam source is X-ray, and this is corresponding to the cosmic ray muon in the case of muon radiography. Detector, in the case of to take picture of our body, X-ray detector is X-ray film. And this is corresponding to muon detector in the case of muon radiography, located here in this picture. And the target is our body. In the case of our study, it's volcano. And the dense part is in the case of our body, our bone is very dense. But in the case of muon radiography, magma rock is one of most dense part. And now I will show how to make a density image. So this is at first the calculate the thickness of the rock from various observation point by using topological demo data. And second, the measure the muon attenuation ratio for each zenith angle. I mean, this is horizontal axis is corresponding to the azimuth angle, and but this particular axis is corresponding to elevation angle. And measure the attenuation for each direction. And the attenuation ratio is we can measure. So then the density by length, let's say the amount of material belonging to the muon path is determined. So we can determine if we can know the penetrating muon flux, we can determine the density by times length we can determine. And projected average density, let's say density by length per rock length, is become final image of the density of rock. This is a very easy and not so detailed, but this is a very easy explanation for the making the image of density image of volcanoes. So now we are using two detectors. This is a detector of opera experiment, one of neutrino oscillation experiment located in Italy, Gran Sasso. And one is nuclear emulsion film, and the second is the scintillator bar array and photomultiplier. In the case of we use scintillator bar and array, we put the scintillator bar like this, and this is one set. And another set, we put the scintillator bar, something like that. And if, for example, muon penetrate like this, we can determine that this point the muon penetrates in this plane. And in this plane, muon penetrates here. So we can determine the direction of the muon. And I think this kind of techniques is very popular in this laboratory. The second is a nuclear emulsion film. Later, Dr. Valeri introduced the detail of these techniques. This is a very, let's say, very sensitive X-ray, kind of X-ray film. And we have been used these two detectors in case of the situation. They have good point and bad point. At first, power supply emulsion films, we don't need the power supply, but scintillator array, we need power supply. And portability, emulsion is light and compact. But we need, in the case of scintillator, we need a large space. And stability for the environment, the emulsion film is very stable for the shock and water and dust and cold temperature. But temperature must be less than 26 degrees Celsius. And this is, I think this is the most important difference. Emulsion films, the image of emulsion films is the integrated image. Let's say the image don't have the time information, and scintillator detector have the real-time monitoring is available. And the last is also very important things, the spread of technology. Emulsion films, this is very minor technique. And maybe scintillator and PMT are a lot of institute use this technique. And the original idea of muon radiography is very old. So a lot of researchers try to find something new, something significant but nothing significant until 2006. The first significant work by muon radiography is to see the volcanoes. This is the picture of Mount Asma located in the middle of Japan. And this is the topographic map. The color variation represents the altitude. So this here we can see the big crater, and about 1 kilometer distance, far from 1 kilometer distance. Now we put the emulsion detector. Put the emulsion detector. And this is the result of the first significant result of muon radiography. At first, horizontal axis corresponding to the azimuth angle. This is also the horizontal distance at the crater center. And vertical is elevation angle. And the color variation is represents the density. We can see the this line. We can see the black masked region and this dotted line. There was the eruption in 2004 in Asama. So when the eruption occurs, the crater before the eruption, the shape of the crater is like that. This is measure. This was measured by radar from airplane. And after the eruption, the shape becomes like this. And then we can see the shallow part of the crater. And we found there is a dense part here, comparing to here, for example. And we thought this is the result of magma is come up here and cool down and fixed magma rock. And second important thing is very low density zone is here. We thought this is a result of a phenomena of magma drain back. And we have been observed a lot of volcanoes. This is Satsuma Iojima, located in the south part of Japan. And the most interesting things in this volcano is continuous gas emission for more than, sorry, I forget, but 1,000 years or 10,000 years continuous gas emission. We can see the lower density region here. And sorry for Japanese character. And there was a convection model in Satsuma Iojima. The red orange magma is, let's say, water-rich magma. So, and this color corresponding to the water-poor magma. So, water-rich magma is lighter than water-poor magma. So, there is should be a convection in this model. And lighter magma go up to here, and the pressure decrease, so they begin to bubbling here. And after bubbling the water, after emission of the water, the magma go down to the deeper part. So before this observation, such kind of theory exists, but now we can see this picture. So we can determine that this theory is right. We can confirm. So we try to. In principle, it's possible to see the volcanoes from the different side. This is the result of Asama stereo observation. The red part is dense part, and the green part is less dense part. And the recent, more important job is the observation of the Niigata seismic fault. There is a very big tectonic line, Itoi-gawa-Shizuoka tectonic line. And here, Itoi-gawa, we put the muon detector here. And fault outcrop is here. This is let's say predetermined fault line. But the predicted seismic fault should be here, but anyone can find this hidden fault. And the geometry, let's say, the next picture is, let's say, the cross section. The typical length of the rock is about 25 meter and 250 meter, and the fault width is 20 meter. And this is very so complicated. So let's visualize that graph. So at first, 23rd in June in 2011, there is a heavy rain, and 4 days after, at first I should explain this color variation. So this is a density color variation. 0 is less dense, and brighter blue is much dense. Much dense means there is a water, and heavy rain in this day, and 4 days after we can see the dense part go down, and after 3 days we can see also the dense part is go down slowly. So we can see not only the static image, but also the water movement we could detect. And this is going now analyzing. There was the eruption in 1991. This is a picture of Mount Unzen from this point of view. After the eruption, there is a big lava dome here. And now we put the muon detector near the lava dome, and now we are analyzing. And Stromboli also we put the detector here. This maybe Valeri-san will talk about this observation later. Anyway, the imaging of conduit is very critical for the eruption dynamics model. So 2 days or 3 days ago, we already put the emulsion detector, the cable car, the top, in the top of the Payday, there is a cable car house. We put the emulsion film 2 days before. So we started observation. And this is another project in Canary Islands. The Tenerife is one of very ideal place to see. Let's say this is mountain and this is horizontal mine gallery, and we put the muon detector here and to see the muon from the sky. So this the first aim of this experiment is to find the geothermal reservoir region. We will put the scintillator detector in this at the end of this March. And also La Palma, maybe this is one of very famous fault because it may occur the very big landslide and big tsunami. So we need the detailed information of this fault. So we will put the emulsion detector here. And this is the fault direction, and we load it here. The fault and detection position is relative position is like this. So thank you for listening. Thank you very much.
Yeah, thank you very much. And maybe we can have like a couple of questions to his talk directly, if anyone wants to ask. Otherwise, we can have the questions also for him after the second talk, because we are running a bit late. So let's welcome our next speaker, Valeri Tioukov.
Thank you. Okay. I will speak about the application of nuclear emulsions as a detector for muons radiography. I work in Italy in INFN, which is Instituto Nazionale di Fisica Nucleare, and mainly occupied by experiments for neutrino oscillation, in particular opera. Okay, a few words about nuclear emulsion as a sensitive media for charged particles. When the charged particle passes the emulsion surface, it leaves so-called hidden image. And after the development, which is similar to the development of normal photographic film, this hidden images becomes the argent grains. The grain size is about 0 to 0.2.3 microns, and this is elementary detection element in the nuclear emulsion. So on this slide we see the path of the MIP particle. MIP, it means minimum ionizing particle, and we have about 30 grains per 100 microns for opera emulsion. Emulsion analysis technique is very old. Emulsion used maybe for 70 years in particle physics, but before 1974, the only way to find the charged particle tracks and the decays inside the emulsion was the visual inspection. So this sympathetic lady passed her life looking into the microscope. But in 1974, Kimio, which is professor from Nagoya University, proposed use the very new at that time electronic method for for tomographic images in the nuclear emulsion. This was the first idea of automatic scanning, but the digital technology was not yet ready at that time. Actually, the first digital camera prototype comes in 1 year later, invented by Kodak. In 1980, was developed the first semi-automatic scanning system at Nagoya, and in 1985 started so-called track selector, new track selector, and so on, development line again in Nagoya University. In 1994, Italian laboratories entered into the emulsion business, and in 2004, the first prototype of so-called European scanning system was developed in Naples. The principle of automatic emulsion scanning is presented on this picture. You see the camera. This is the digital camera that based on CCD or CMOS sensor. The optics of microscope, and you can take one by one the layers inside the emulsion volume. And what you get, the sequence of images, which is one small fragment is presented on this picture, which is actually the tomographic image of everything which is inside the nuclear emulsion. So we are looking for these small grains. Here you see what is the microscope looks in the nuclear emulsion. These small dots, some of these small dots represent the tracks which crossed the emulsion. So here you see the decay point, and there are tracks coming from this point. Only the small part of this information is useful actually. Most of the dots are all randomly distributed fog or electrons or some other background. Here is a block scheme of the data flow in the scanning system. Well, I will not stop here much. And here there are the photos of two systems, Japanese developed in Nagoya, and European scanning system on the left. Both systems, well, the difference between these two systems, that in European system we use the commercial optics and mechanics. And in Japanese system, a lot of parts are customized, and it's based on FPGA hard-coded algorithms. Japanese system is more performant, but it's more expensive. And the European system is very easy to clone. Both systems demonstrates 0.3 microns spatial resolution and about 2 milliradians angular resolution, and very high efficiency for minimum ionizing particle tracks. This is in detail. So you see here the camera, the optics of the microscope, objective, and the emulsion plate, which is here. This is the stage which can move in both directions, and this stage can move vertically. So we can take three-dimensional tomographic image of a volume. There are quite a big number of these systems developed mainly for neutrino oscillation experiments for Chorus and Opera. In Europe, there are about 30 systems, European scanning systems. There are several systems in Nagoya. And these systems were developed about 7 years ago. And now new generation of scanning systems are coming, and it will increase 1-2 order of magnitude of scanning power. And just to give you an idea of our main experiment, this is Opera. And this is about 10 by 10 by 50 meters construction, which consists of 2 supermodules. Each supermodule here there are the emulsions. In each of these cell installed the line of this kind of bricks, which are bricks of lead emulsion of 56 layers, and the size is about 12 by 10 by 8 centimeters. These walls are interleaved with walls of electronic detector, so with scintillation detector walls. Here, this is an example of opera emulsion film. There are 2 sensitive layers of 44 microns and 1 plastic base with 2005 microns. When emulsion passes here, we can see the dots on her track. Opera emulsions has tuned for minimum ionizing particle detection, and it has a high sensitivity. This emulsion already developed for opera detector has extremely high angular resolution and high muons detection efficiency, and this makes them very good for muon radiography. So in emulsion, in opera, you see there are 8.9 million of films installed, and the total surface of all emulsion films is about 100,000 square meters. So it's a huge with respect to our detectors. Some numbers concern the emulsion scanning. Emulsion can be considered as a multi-layer optical storage media, like a DVD disc, for example, with a storage capacity of about 1 terabyte per 100 square centimeters of image information. And the typical area of detector to be used for muon radiography is of 1 square meter, and considering 4 emulsion plates, which is necessary for patterns matching, and 2 sides in 1 emulsion plate means about 8 square meters of emulsion surface. This corresponds to about 800 terabytes of image information can be processed. The speed of European scanning system is about 20 square centimeters per hour, and which means about 1,000 hours, 4,000 hours of scanning for one system. But of course, several systems work in parallel, so we can finish the scanning in a few months. As I told, this is the old generation of scanning systems. This is to give you the idea of the post-scanning processing. So we reconstruct the segment, emulsion segment, track segment here in one emulsion. Then we have several plates. In each plate we have a lot of segments reconstructed. After the pattern matching, you can get the passing through tracks. And well, it refers to the opera. We are looking for the case, so we can reconstruct the vertex using these tracks. And this is the final product of opera experiment. So this is tau decay registered in the emulsion. So we see here the decay point, and the particles, and here is the king of the tau. Okay, now concerning the application as Murray detector. There are several advantages and several disadvantages, and Miyamoto-san already explained most of them. I will stop mainly on this disadvantage, no timestamp information. So in electronics detector, when a particle passes through the detector, you know exactly when it's happened. In emulsion, all particles are accumulated. So you produce the emulsion, you bring it from Fuji, for example, to to Tenerife, and during his life, during the emulsion transportation, a lot of particles comes inside, a lot of muons and all other particles. So after installation, and the number of particles can be more than we will get after installation. So how to distinguish between useful, let's say, signal data and all the rest? The secret that we use the independent emulsions, which after assembling stay in very fixed position. So emulsion accuracy is about 1 micron. So with a 1 micron accuracy, we can register the direct lines after the assembling. So when we extract the emulsion and disassemble them, emulsions are developed and when scanned, and we found a variety of tracks in one and in the second. Here there are the signal tracks, and there are also a lot of background tracks. After that, we start a procedure of pattern matching. So, for example, which is very powerful. For example, on this here you see about 30,000 of segments in one pattern and in our pattern. And here in this case, we look the signal of 30 tracks, 30 coincidences. And using the pattern matching algorithms, we are able to distinguish this is a transportation background, and this is as our signal from a very short exposure to cosmic rays of about 30 tracks. This is the way why it's possible to extract information, the useful information from the emulsions. And this is why we put several layers for several independent plates into our detector. So, for example, for Stromboli exposure, we used the model presented on this scheme. Here you see for each of this block is one envelope with emulsion inside, and there are independent envelopes 1, 2, 3, 4. So this is one cell. It consists of 4 independent layers. So after the pattern matching, we can, with very high purity, unambiguously define the tracks which pass after the assembling, so after installation of our detector. This is the example of our model which we install on the Stromboli. Here you see the envelope with emulsion inside. We need envelope, of course, because the emulsion is a kind of photofilm and it's sensitive to the light. This is the detector installed in the position. And a few words about the analysis which we do to this data. On this picture you see Monte Carlo data. So the input data for us is the flux of the atmospheric muons and a digital elevation map of a mountain. So here is the detector position, and here is our region of interest. On the Stromboli, it's so-called Shara di Fuoco. Using these two information and assuming some mean density of a mountain, we can first of all calculate the rock thickness And the second, to calculate the muon flux expected in our detector. So we have this stuff coming from this direction, it passes through the rock and reduce it and finish here. And we should see here the angular distribution like this one. Here is the vertical angle and the theta angle and the phi in milliradians, in radians actually in this picture. And the color is the intensity of muons. And here you see the photo which I made from our detector. This is our detector. It's actually the detector itself. It's like a photograph photo camera directed to a mountain. So from here we see the slope of a mountain, and here is the zone of interest which we are hoping to study. And this is already processed data. For a moment to process only 10% of our statistics, but you see here it's following exactly the shape of a mountain. So we see the mountain with muons. What we are going to see is some structure in this zone. And this structure will be visible only after the application of Monte Carlo data. So we should compare this flux with the flux from Monte Carlo data. But for the moment, the statistics is not yet enough to get this kind of resolution. Okay. So my conclusion is that nuclear emulsion, which used in a long time for particle physics, appeared to be well suited for muon radiography thanks to its high resolution and simplicity for installation and handling. Automatic emulsion scanning systems developed for big HEP experiments makes possible analysis of a large detector area of several square meters in a reasonable time, and a few months. Next generation scanning systems coming in approximately 1 year makes possible to reduce the analysis time from months to days, and this could be a big boost for muon radiography also with this technique. Okay, so we hope soon to see something in this zone of interest and share the foco, and thank you for your attention.
Yeah, thank you very much. Do we have any questions?
Well, I have a very simple question. You have mentioned the surface that is used, for instance, in the opera experiment, which is very huge.
Yes.
Which is, I suppose you have to somehow make a sort of simulation to know how big has to be the area in order to be able to have a good resolution in your modeling, in your post-processing of the images. In the case of the Teide or La Palma, how big is the collecting area that you plan to use?
Well, in the case of Teide, we installed a detector of about 1/2 square meter. And it should be enough because actually the resolution depends on several factors. One is emulsion surface, of course. The second is the rock thickness. The third is the dimension of the target. So how big resolution you need to see the structure that you want to see. And in case of Teide, the rock thickness is quite small because we are close to the target. That's why 1/2 meter, 1/2 square meter should be enough. But for example, in case of Vesuvio is huge, and In this case, we will need much bigger, if one decides to do the muon radiography of Vesuvio using the emulsions, the detector surface should be maybe 10 or more square meters.
In the case of the volcano you already studied, how well or how bad your results correlate with the gravimetric density model?
Well, I think it's a question mainly for Miyamoto-san, because for what concerns strombol exposure, which let's say are directly involved into the analysis, we still not have enough statistics to make this kind of conclusions.
Sorry, I can't hear your question, so pardon me.
Many volcanoes use density models constructed by the result gravimetric all around. And they make model of density at elevation. So, how well do you result? To result
So as you know, the various geoscientific instruments to see the inside of the rocks. For example, seismic sensor is one of them, and also the to see the current in the rock is another instrument. And the third is, you said, gravity measurement. That is, so now it is very difficult to compare for example, seismic image reconstruction and muon radiography density reconstruction, because the seismic imaging is depends on the velocity of the wave, and in other case, in the case of muon radiography, the density. So it's difficult to compare the results. So, but we have good agreement with the gravity. Gravity is have sensitivity for the density. So now we can compare the density, but we will continue to make a good agreement with the, for example, seismic result and the muon radiography graphs. We will.
Okay.
Maybe I can add that different methods has different resolutions. So I'm not an expert in gravimetric measurement, but I can imagine that the resolution is maybe several hundred meters or kilometers or kilometer size, maybe. And here our resolution is smaller, so maybe it's not so easy to compare. Our resolution is tenths of 100 meter, so it's 1 order of magnitude less.
this is even much more resolution than
Yes, much more resolution, but of course we cannot see very big masses, which are typical for gravimetric scale.
Okay. thank you very much. And yeah, let's thank both of our speakers once more. And yes.